So the first thing I want to just briefly mention today are recovery plans. I don't have the recovery plans out yet. I've started the process, but I didn't get through them all yet. Tomorrow, for sure, at the latest tomorrow night, I will not go to sleep tomorrow without having them all done. I'll go through all the recovery plans. So if you didn't complete all 3 portions of Learning Objective 1, you'll get a recovery plan from me outlining what you can do to make up those things. This will include deadline extensions, another interview chance, another quiz chance, etc. I don't know all the details. It will potentially be different for each student. So these will be on an individual basis. You all get your own recovery plan, but there will likely be lots of similarity between them, just because most of you will be in very similar situations, and I'll have the same, like anyone who didn't complete the project yet is probably going to get either the same exact or very similar extension. Here's your new extension deadline. Complete it by then, and if not, then we got to have a unfortunate conversation kind of thing. So you will get those. You will get those by Tuesday, by tomorrow. I'll get those out. I wanted to get them out this weekend, but I had quite a bit of real life stuff, family stuff I was doing. I never get into office hours. You got to be patient with office hours. For my office hours personally, I will always see every student who's in there, but a lot of students give up and just leave the meeting. If you're leaving the meeting before you're called in, then you're obviously never going to get office hours because you left. But if you stay in there, at least in mine, I'll stick around. I'll at least say hi to everybody. I might not give you a lot of time, but I'll at least say hi to everybody who came and waited patiently. But being coming close to a checkpoint last week, I had 20, 30, I forget how many students. Last students. Okay, let's get into... You don't have to leave to be polite, Lean. I mean, everybody deserves time. Everyone deserves to be seen. Can we reduce the time everyone gets to 10 minutes? No. I mean, for me, I don't usually spend more than 10 minutes, but I mean, when there's 20 people in the queue, and in 10 minutes, do you want me to cut you off at 10 minutes? If we haven't gotten to the crux of your problem, we're almost there, and I'm like, sorry, bad boy, it's 10 minutes, so see you later. I'm sure you're going to complain about that. But I'll stay, last week I stayed, I think 45 minutes past my office hours just to make sure I saw everybody. Just be patient. So, I know that's tough, but especially on Zoom, you can do other things while you're in the waiting room. Just leave your speakers on when you hear me talk. It's your time. All right, so let's get into content. I don't want to spend too much time talking about logistical stuff. Let's get right into inheritance. So the lecture task today, it looks like a lot of text. Don't be frightened by this one. And actually, the entire homework 2, it's homework 3 and 312, homework 2 and 116. The entire homework 2 is a lot of text, and you shouldn't let that scare you off. This one I don't think is too difficult. It will test your understanding of inheritance. But beyond that, there just has to be a lot of text because we're creating 4 different classes to really explore what inheritance is and what it does. So for this one, for the last lecture question, we added sales. So we could add sale prices to our items. And this time we want to be able to add those not to our testing item, but to our core item class that we're working with. Eventually, that'll be lecture task 4, actually, on Wednesday. But we want to eventually add sales and other things to our items that we're going to sell. Now, sales are cool, but we want more than just sales. We're going to have sales, we're going to have sales tax, and we're going to have bottled deposit, all that can be applied to an item that's sold, which is going to affect the way it checks out in our checkout machine. There are also, if you do the application objectives, 2 of the application objectives are to add a 4th and 5th modifier, which we're going to call these 2 items. So all these are kind of similar, that they're all going to modify how an item is rung up when it's scanned. So we're going to have all of these inherit an abstract class that we create called modifier, and we're going to have these as general. We're going to have a term for these and call them generally modifiers. So we can add a sale as a modifier that modifies the price of an item. We can add sales tax as a modifier, which adds tax to an item, and we're going to have these two methods: update price and compute tax. Sales tax will add tax to the item, and bottle deposit is going to add a bottle deposit as a tax. Which I got this question a few times. I didn't really expect this too much, because when we're on campus, it wouldn't matter as much. But what is bottle deposit is a question I got a few times. So if you're not in New York right now, you might not be aware of this, and you can't. If you were in New York, if we were on campus, I would just say go to the store, buy a bottle of water, and look at your receipt, and you'll see the bottle deposit of 5 cents on that bottle of water that you bought. This is a kind of a New York thing, but a few other states kind of a Northeast and California thing, I guess. But a good amount of states have a bottle deposit. So every time you purchase something that comes in either a bottle or a can, for most types of bottles and cans, they're going to charge you either 5 or 10 cents per bottle or can. And that money is collected by the retailer, but it goes to the government. It goes to New York State in our case. And then you can take that bottle or can back to a recycling center, and they'll give you that 5 cents back. So it's a way to encourage us to recycle, just something that we live with in New York State. And that's added, for our purposes, we're going to add it as a tax. It actually is its own separate thing, but we're going to pretend it's a tax. So we're going to add it to the tax line. And now, since we're all online, we're not all on campus. Some of you are in India or China. You never really heard of the concept of a bottle deposit. And I can't just say, go to CVS on campus and buy a bottle of water. You'll see it on your receipt. But if you are in New York or one of the states that have a bottle deposit, take a look at your receipt next time you buy something that comes in a bottle or a can, and you'll see it right on your receipt. Actually, I meant to bring one up today. I would hold it up to the camera and show you. But it'll say right on there, New York State bottle deposit, 5 cents per bottle. So if you buy a 12-pack of pop or soda, you're going to see on there bottle deposit 60 cents. And that goes right to New York State. And then we can get our money back when we return our bottles. But in general, we have these different modifiers that can alter how an item is going to be rung up in our register. And I saw the question, what is inheritance? And usually I'll try to be consistent with this, but I'll bold the words that you're not supposed to know yet. So abstract class, the hell is that? Inherit, what does that mean? Override, implement, I guess I didn't use the word override. What do any of these mean? We don't know yet. So let's go in today's lecture. Oh, and testing, I didn't mention testing. A few of you asking for that. Testing. I can talk about this more at the end. I have a bonus slide in today's slides if you want to take a look at that one. So let's get into this and learn what these things are. And I'm going to increase the mystery just a little bit here and tease you with this chart. The type hierarchy in Scala. So the type hierarchy, everything, every class, every type in Scala extends this any type, and then we have certain values, certain types, which are what I call our primitive types, because they compile down to JVM primitive types or Java bytecode primitive types. These all extend a class called anyVal. These are all the types that go on the stack, and everything else extends anyRef for any reference. These are objects that are stored and passed by reference. These go on the heap, and they extend anyRef implicitly. Still, what does extend mean? And I'll pull up this chart again at the end of lecture, and I'll say that again, and it'll make more sense at the end. So let's get into this and start exploring what extend and inherit mean, are two of our big vocab words today that you'll start hearing throughout the rest of the semester. So let's explore this through example. And let's do the setup for a bit of a game. I don't know if we'll ever implement this game. We may or may not see this game really realized. And it's similar to using the player class that we've seen before, but just another example where we can explore these topics. So let's imagine this game where we have a 2D top-down view. We have players that can move around in this top-down view. They each have a health, which will follow the max health and HP that we saw before, a strength, value, and they can interact with two different types of objects, either dodgeballs, which they can find laying around, pick up, and then throw. They can get hit by dodgeballs and lose health, and they can also interact with our second object, health potions, where they can consume those, walk over them, and consume them to regain some health. So we might not see the whole game, but this is the game we want to imagine. These are the features that we would want, and this is the gameplay that we would want. We want multiple players running around, picking up dodgeballs, throwing them at each other, and then finding health potions when they lose some health, so they can regain that health and continue with the game. And then if they run out of health, you're out of the game, things like that. We could add those features. Today we want to focus on these two types of objects that a player can interact with: dodgeballs and health potions. The parallel here, I'll be upfront with this. The parallel here is that dodgeball and health potion, these are two similar types. And we're going to use inheritance and see how we're going to use inheritance to work with these. Very much like sales tax, and battle deposit are three very similar types. And you're going to use inheritance by creating a modifier class that they all extend. We're going to create a third class that dodgeball and health potion both extend. So watch for the parallels with the lecture question as we go through this, as we explore this example. But dodgeballs and health potions we'll really want to talk about. First, let's do a little bit of review. Since objects and classes specifically, are pretty new to us still, let's do a little review about classes and see why we use classes. So let's reimagine our player class as a different class than the player we've seen before. We have a little bit different functionality, some of the same functionality, but just a little bit different to motivate this particular example. This player is going to be in a 2D space. Yes, you need LT2. All the LTs build upon each other. You'll need LT2 for LT3. This is players in a 2D space with a location in the 2D space, an orientation, which is the direction that the player is facing. So this player is at, if you think of this as an origin of the axis system, 2, -2, the player is right here and facing 0.5, -0.5, so the player is right here and facing this way. So you can think of it like that. If you don't want to think about that at all in the actual physics of this, don't worry about it, don't sweat it. It's not too critical to what we're doing today. So you can think of that as where the player is in this 2D space and which way they're facing in this 2D space. There's some health and max health, some strength value, and two methods that allow the player to interact with the two types of objects that we have in our game, both dodgeballs and health potions. They can use them. Each one of these types is going to have a use method, which takes a reference to a player, which we're going to pass using the keyword this. And then dodgeballs and potions in those classes determine their behavior when they're used by a player. So a player doesn't care how these things function, but they are going to pass the functionality, pass that behavior on to dodgeball and health potion. The physics vector, it doesn't really have much functionality. It's just going to store the X and Y location. There is a physics vector in the repo, but I did change it a little bit for this example. The physics vector in the repo, it has X, Y, and Z. It's a 3-dimensional vector, but there's really not. I don't think there's any functionality in there in the repo. It's just a vessel to store our locations in this Euclidean space, in this on this grid system. Yeah, and this would work with the physics engine homework, but we're not doing physics engine in this class, so I modified the slides a bit just to simplify it, since I know you don't have the physics engine background at all, since I've never even mentioned it at all. They are doing it in the other section, so if you're in the other section and checking out these lectures, you kind of know where this fits in. But I did change some things, so these slides don't really fit in with the physics vector anymore. Physics engine is a lecture task. Oh, maybe someday. Okay, so that's the player. Let's create a dodgeball object, because we need an object that has a state and behavior. So for a dodgeball, let's just say we want to, and I'm somewhat making some of this stuff up, so don't take it too seriously what is actually in these classes. We're just setting up the motivation for inheritance. So dodgeball, I want to remember its location, in this 2D space, and its velocity. How fast is it moving and in what direction? Right now, I'm going to set the velocity to 0, 0. So this ball is at location 1, 5, and it's not moving at all. And I want to know the mass of this dodgeball. So this is the state of the dodgeball. Its location, velocity, and mass. That's its current state. And its behavior when a player uses a dodgeball, we're going to set the velocity of that dodgeball to a new vector where the x of that velocity is going to be the player's orientation in the x direction times their strength, and the player's orientation in the y direction times their strength. So whenever a ball is used by a player, we're going to say that it moves, it's thrown, in our case, in the direction the player is facing at a magnitude relative to their strength. So a player with a higher strength value is going to throw the ball faster in that direction than a player with a smaller strength. I want to say attribute, but I got a smaller value in its strength state variable. A stronger player is going to throw that ball faster, but they're always going to throw in the direction that they're facing, and at the location that they are. The location should be equal to the player's location if their player's holding the ball, etc. We're not building out all the little details of this one. We don't want to get hung up on all those details. Shouldn't it be def used? No. Use. You mean with the D? No, it should be used, not used. Just to stay consistent with how I called it over here. And finally, we want a health potion class. Our health potion is going to have a location and a volume. We're going to say how big this health potion is, and that's going to determine how much health is restored when this health potion is used by a player. So when a health potion is used by a player, we're going to set the player's health to their current health plus the volume of this health potion. So we're going to say there's a 1-to-1 to volume to hit points healed for a potion. And then make sure that they don't go over their max hit points. We don't want a player drinking a potion and then getting more than their max health. Ooh, yeah, we can pass this as a parameter. Yep, this is just like any other, like Dodgeball is a variable that stores a reference. This is just like any other variable like that. It's a variable, or a keyword rather, that stores a reference. It's a reference to the object that you're currently in. So this just passes that reference. So we can do anything we want. We could say val player of type player equals this. Perfectly valid. And then that stores that reference in a new variable that refers to the same thing that this refers to. We can do all kinds of stuff. Anything that we can do with anything else, any other reference, we can do with this, with the keyword this. So we have our 3 objects. Go us. We built this game, obviously without all the structure and all the details surrounding it. But we set up the structure, or we set up the objects of our game. But this is extremely restrictive. This is a really boring game. Because we set these up as objects, we can only have one player. This is a single player game. There can only be one dodgeball, and there can only be one health potion. We define these as objects, so there can only be one of each. So you could play this game if we built out the rest of it. It would be super boring. Where you're going to throw the dodgeball, try to get it to bounce off a wall and hit yourself just so you can pick up a health potion and restore your health. Super boring game. Nobody wants to play this. The doctor, that's an excellent question. What's the difference between class and object? So this is objects. There can only be one of each object when we declare them using object. So we declared objects here. Object, object, object. We got 3 objects. We can only have one of each of these objects, which is boring, which is why we created classes. So we create classes, which are templates that are used to create objects. So if we create a player class, a dodgeball class, and a health potion class, now we can have many players. We have a multiplayer game. We got many dodgeballs. We have many health potions. We can use these classes to create multiple objects of these types. That's why we use classes. So to transfer this over to classes, let's rewrite these. Have a class with the same state and behavior, but we're going to set that up as a class and not an object. Since these are now classes, we can have constructors, which are going to be called when we create an object of this type. None of our objects could have constructors because there's only one of them. It's created, it's initialized. There's no constructor. You never say new object of an object type. With the class, we're going to say new player and then call the constructor. So any of the state that we want to be able to initialize when an object is created, we're going to put those variables, that part of the state, in the constructor. We're going to choose var, val, or neither when we declare these variables. If we use var, it can change. Val, it can't. If we use which we're used to, if we use neither, the value cannot change, but it also can't be accessed from outside of the class. So if we want other classes to be able to access these variables, for example, max health was accessed from the health potion class, player.maxHealth, we wouldn't be able to do that if we didn't use val or var here. So we use val to make sure max health is accessible from outside of this class. So, and we want all these variables, all these to be accessible outside. So we use either val or var depending on whether it's going to change or not. Max health, we're not going to do any level ups or anything. So max health and strength will stay the same. Orientation and location will change as the player moves throughout the space. Health, we never want this to be initialized any differently except being set to the max health. So everybody starts at max health. We've seen this in our other player example. Health is going to start at max health. And then our behavior stays the same. All this code is exactly the same. Dodgeball, our location, velocity, and mass, we're going to allow people to initialize. And no state that is not initialized through the constructor. So we're going to put everything in the constructor here. The behavior, again, stays the same. And then health potion, everything goes in the constructor. We want people to be able to set the initial location and the volume of a health potion. Behavior stays the same. So now that we have 3 classes, we can use these classes to create new objects and have multiple objects of the same type. So with our dodgeball class already defined, we can say new dodgeball, give the constructor its parameters, give arguments to match its parameters. Here we're going to set the initial location at 1.5, the initial velocity at 1.1, and the mass to 5.0. So we create a new dodgeball. We get a reference to a dodgeball. This creates a dodgeball in the heap. We get a reference to it. Again, I just made up numbers for these. We get the reference and store that in a variable, and dodgeball 1 stores that reference that says how to find this dodgeball in the heap. We create another dodgeball, dodgeball 2, and that's going to store the reference of wherever the next dodgeball was created. So we have references to 2 different dodgeballs on the heap, and we can do all of our object stuff with using these references. And most importantly here, we can have multiple objects of the same type that have similar behavior, identically defined behavior rather, but different state. They can have change state independently of each other. And then their behavior changes based on their state, but the code of the behavior is the same. So everyone good on classes and objects review? Can an object have a class? Ooh, that is a trippy question, An object can have references to other objects, like physics vector is also an object, something I didn't show on the slides here. So dodgeball actually has, and I showed this just as the XY, but actually location would store a reference to a physics vector, which would be somewhere else in the heap. So an object can have references to other objects, but it technically, I'll give it one of these. Technically, an object can have a class defined within it. It's just not something we're going to do in this class because we really don't need to get into that stuff. But like in our object, in an object here, like outside of all the methods, we could say class of some type and create a brand new class inside an object. It's not something we want to do. It's really not something anybody should be doing very often unless they have a very specific reason to do that. I'm not sure if that's what your question meant, but you could do that. Oh yeah, priest. Yeah, it should. And I mentioned that you posted that before I said that just now. But yeah, these would be references to physics vectors. So I did shortcut this a little bit. But there would be 4 extra objects because I created new physics vectors. Each physics vector will be its own object on the heap with its own reference. Location and velocity here would store references to those physics vectors. I did shortcut that a little bit. Maybe I should have, just to show that we said new 6 times. That means we created 6 objects on the heap. I should make that more clear. It's just not what I was thinking when I made these slides because I was focused on inheritance. So let's talk about inheritance. So that's our setup. That's our review. That's our setup for what we're talking about now. But we noticed that Dodgeball and Health Potion have similar state and behavior. They both have a location, and they both have this use method that takes a player and returns unit. So what we want to do with inheritance is create a third class that has all of the common state and behavior factored out of Dodgeball and Health Potion. And then Dodgeball and Health Potion are going to inherit all of that state and behavior from that third class. So and we can have a lot more here. We just have location and use, so not a ton here. But we could have a lot more state and behavior that we want to factor out. We have 2 similar classes. The common similarity between Dodgeballs and Health Potions is that they are objects in the game that a player can interact with, and they have to have some location within this game. So let's take advantage of that and factor out that functionality. Just like in math class, we're going to factor out all the commonalities here into a separate class. So I'm going to name that a GameObject class. So Health Potions and Dodgeballs are both going to be game objects. They're objects that interact with my game. Just like sales tax, and bottle deposits are all modifiers that can change the behavior of an item by altering its price and its total tax. So let's factor all the common behavior out into GameObject. And I'm also going to add another method here, this object mass, that returns double. Now notice this doesn't exist in Health Potion anywhere. There's no sense of mass. Dodgeball does have some mass, but Health Potion has no sense of mass. But we're going to add this to our new class that we're creating, and we'll see what consequences that has down the road. So we'll factor out all the common state and behavior, and then inherit this class from both Dodgeball and Health Potion to get that common behavior. So what does this look like in our code? We're going to create GameObject as an abstract class. What this means is that this is a class that is not fully defined. When we have an abstract class, we can never create a new object of this type. This isn't a complete type. We can never say new GameObject of some physics vector. We can never do that because it's abstract. It's not fully defined. And we actually have a few methods. You can see here, these are methods that don't have any definitions. We just said def object mass takes no parameters. It has type double. And then I just stopped. I'm like, I'm not going to say equals and then braces and give it a body. I'm just going to stop. That's what makes this abstract, is that these methods are not defined. So since they're not defined, I didn't finish writing this class. So I have to call it abstract. If I just said class GameObject without abstract and didn't implement these methods, I'm going to get a compiler error. It's going to say, hey, what are you even doing? You wrote half a class and just stopped. Like, cut it out. Either implement the methods or call this abstract. You just write it. So when you create a new class in IntelliJ, like you have the drop down that says object or class or whatever, that's just to help you out. IntelliJ is trying to help you a little. If you create a new object, for example, and you just delete the word object and write the word class, IntelliJ would be like, oh, you want that to be a class now? I got you. So if you create a class and just type the word abstract space, if you just type that right in front of it, IntelliJ is going to say, I got you. You want an abstract class there. There's no magic behind when you create the object. All that does is add the word either object class, abstract class, or anything when you create it. It doesn't really do that. There's no magic behind the scenes that it's doing for you. Yeah, exactly. Repetition. If a class is a template, an abstract class is a rough draft. It's a good way of putting it. Okay, so this is an abstract class. It's not fully defined, and it has some abstract behavior. Now we're going to inherit this in other classes, and it's going to be those other classes' job to implement these methods. So these abstract methods have to be defined by the time we say new something of this type. That type won't be GameObject. It'll be health potion. It'll be Dodgeball. But by that point, we have to have these methods implemented. So by defining, you might ask, why even put these here? This is pointless. There's no functionality. GameObject doesn't really do anything, which is pretty true right now. This is still useful, as we'll find out on Monday. On Wednesday, we'll explore. But there is a good reason to do this right now. What this is going to be is, yeah, exactly. This is leading into polymorphism on Wednesday. If you want my hot take, inheritance is fairly useless. I mean, I motivate a few ways here, and that's absolutely true, but it's not that motivating. Inheritance enables us to use polymorphism, though, which is where things get really powerful. With polymorphism, we can really do some cool things. But we need the setup of inheritance. Inheritance itself is pretty cool, but, I mean, would we do inheritance if this is all it did? I don't know. But with polymorphism, there's so many things we do with polymorphism that we couldn't do. Unlimited cosmic power when we get to polymorphism. Not to downplay this lecture, but once we start using polymorphism, Scala has multiple inheritance kind of through mixins, but you can only extend one class that has a constructor. All the other mixins have to not have constructors. So we have these methods that don't have definitions. So what's the point? The point is that every class that extends this class, this abstract class, has a contract that it has to implement these methods. There's a guarantee that if you extend GameObject, which we'll see on the next slide, let me just click to it. If you extend GameObject, you have an obligation to implement these methods. You have to implement them in order to be able to be a class, what we call a concrete class, which is a class that you can create objects of. So if we don't implement these methods, we're violating that contract, and our options are either just implement the things or have Dodgeball also be abstract, which means we would never be able to create Dodgeball objects. We want to create Dodgeball objects, so we're going to implement them. So here's where inheritance comes in. We want Dodgeball to inherit all of the state and behavior of GameObject. So we're going to use this keyword extends, and right after the Dodgeball constructor, we're going to say extends the type that we want to extend. In this case, it's GameObject. We're going to say extends GameObject, which can be read inherits GameObject. Extends GameObject, and then call the GameObject constructor. So we're effectively, kind of somewhat implicitly saying new GameObject right here because we're calling the constructor, but we're doing it through the constructor call of Dodgeball. And any constructor parameters of Dodgeball are in scope here. So here we get a location in the Dodgeball constructor, and we forward that location to the GameObject constructor. So we're calling a constructor with an argument that was a parameter to another constructor. We have two constructors in this line. One defining a constructor and one calling a constructor. And that's our syntax for extending or inheriting from another object. One thing to note when you're calling these, when you have these multiple constructors, is that if you're going to duplicate names, like here we have two variables named location, at most one of them can be declared with either val or var. This is one of them kind of gotcha things that can trip you up and have really mystifying errors in your code, is you can only have one of them declared with val or var. So this dodgeball, when it extends GameObject, it is inheriting all the state and behavior of the GameObject class, which includes a state variable named location. So in the dodgeball class, if we say this dot location, what do we get? Do we get this location, or do we get this location that was inherited? I don't know. It's a good question. If we used val or var for this location and we were outside of the dodgeball class and said dodgeball1.location, which location are we going to get? How is the scoping going to resolve there when we have two locations with the same name? I don't know. Good question. Scala says no, don't do that. You're only going to have one val or var. So var, this is the location variable that's accessible from outside of the class. And then inside the class, these will actually have references, in our case here, references to the same object. So we don't have to really worry about it. The best thing to do here is just name them different things. I wanted to name these the same because it's common that you're going to do that. And if I see that in office hours, I want to be like, hey, remember when I said that in lecture? So I named them the same here. So only one of them can be val or var, so we don't have naming conflicts. Velocity, mass, these don't exist in the GameObject, so I don't have to worry about such conflicts. Everyone good with that? So dodgeball, the class dodgeball that we're defining, we gave it a constructor, the same constructor it had before, except we're saying, also, I'm going to define some stuff here, but also give me everything from the GameObject class. Everything in there, and here's its constructor parameter because it needs no do you have a specific? Because I know this is a lot, and we'll spend a while digesting this, at least obviously the rest of this lecture. Why doesn't mass use val or var? Because I'm not going to... So mass, by not using val or var, I'm saying mass cannot be accessed from outside of this class. Only this class is going to be able to access mass. But I get around that by returning it through object mass. So if anybody outside of this class wants access to mass, they're going to have to call object mass to get it. You can't say dodgeball1.mass. You can't do that. Why did I choose the same name for the constructor? I didn't have to. I could use a different name here. I did it to show the point that you can only have one of these as val or var. If I say var location here, I'm going to get a compiler error, because now I have a variable that I'm declaring named location of type physics vector and a variable of type location of type physics vector named location, both in the same class. Because when Dodgeball extends GameObject, that means Dodgeball is inheriting everything from GameObject, which includes this variable named location. So if I name this something else, no matter what I name this, down here I can say this dot location, and that's going to access this variable over here. Dodgeball also inherits these methods from the GameObject class. I should have a slide on this. Yeah. Also inherits these methods from the GameObject class. So you can think of this when you say extends GameObject as taking all the code inside the GameObject class and cut and pasting it into this class. That's what extends is doing. It's doing a cut and paste for you and grabbing all of this behavior. And any variable. I don't have any variables, state variables declared outside of the constructor, but it gets those too, and it gets the constructor parameters. So all of that is copied into the Dodgeball class. Problem is, object mass and use don't have any definitions, so it's the Dodgeball class's responsibility to create those definitions. So we're going to create those definitions, and for this we're going to use the override keyword, which means whatever behavior I inherited from GameObject, I want to override that with this behavior. I want this to be the behavior. I don't want the behavior of whatever I got from the GameObject class. What's up, Jake Ryan? So I don't want any of that behavior, which happens to be nothing in this case, but I want to erase that and override it with the code that I'm writing right here. So, and now I've implemented both object mass and use, so I don't have to have Dodgeball be abstract. I can have this be a class, and now I can say new Dodgeball, and this is all of its state and behavior. All of this plus all of this is in the Dodgeball class. We're using inheritance for LT3. Hell yeah, you are. Yeah, you're using inheritance for LT3. So you create the modifier class and then extend that through those 3 other classes that you're writing. And we do the same thing for health potion. Health potion is going to extend GameObject. We have to implement object mass and use. And here, object mass, we didn't have any sense of mass in the health potion class before, but we do have a volume. So we're going to say that the mass is going to depend on the volume. For each unit of volume, we're going to say there's 7 units of mass, and then return the volume times the mass per volume. And that's what the mass of a health potion is going to be. Yeah, exactly. So in testing, we extend FunSuite. FunSuite has a lot of functionality in there for testing, including the test method, which we call to create your testing, which uses a little different syntax. You give it its parameter, which is the name of your test as a string, and then you use braces to give it some extra code in an initializer. But that's exactly what you're doing with FunSuite, is you're inheriting all of the state and behavior that's defined in FunSuite. That's in your class now, and then you're adding additional code of your own, which is the testing. And then FunSuite is designed to work as a test suite and work with Scala test. So we'll do the same thing in Health Potion. We implement these methods. We have a contract, if we're going to extend GameObject, that we have to implement object mass that returns a double and takes no parameters. So we defined that, and we said this is what the mass of a health potion is going to be. And now we have methods, the use method also, but we have 2 methods. For example, object mass, which each of these had to implement because they extend GameObject. But these methods have different definitions based on the type of the object. If I have a dodgeball, object mass is going to be this. It's going to return its mass directly. If I have a health potion, object mass is going to return 7 times its volume. So I have different behavior based on the type of the object, even though they both extend the same game object. Oops, I have a little typo here. Dimensions and velocity should go away. I had a lot of extra clutter in these slides. I cut some of it out. Dimension and velocity was such clutter. I forgot to delete it right here. All right, but why do we do all this? It seemed like we just did more work. You could argue that what we've done so far was just more work to get the same functionality, and we saw 0 benefits. So let's motivate this a little bit and ask why inheritance. We'll see a little bit of motivation here, and then of course polymorphism, the big motivation on Wednesday. So why do all this? So one reason, we didn't have much in the GameObject class. We had no defined behavior and only one state variable, but we can add more behavior or variables to this class. And when we do, say we want this close to player, we want to figure out a player's running around in the game world, and maybe that when they're close to one of these 2 objects, they automatically pick up the item and add it to their inventory, something like that. So we want to know when an object is close to a player, and we're going to check, is this object close to this player? Compute the L2 distance, and the Euclidean distance, whatever you want to call it. And if that's below some threshold, we're going to say, yes, this object is close to a player. When we write this in the GameObject class, and this is not an abstract method, it has a definition. It's fully defined. We can do that in abstract classes. Abstract classes can have fully defined methods. When we fully define this method in the abstract class, Health Potion and Dodgeball automatically get this behavior because they extend the GameObject class. So we want to add this behavior. These two classes that we have, we want them both to be able to detect when they're close to a player. No problem, we'll just add it to the abstract class that they both inherit. They already inherit everything from GameObject, so anything we add here is also inherited in those classes. So now Dodgeballs and Health Potions can both tell when they're close to a player by calling this method. So adding auto pass if you get a Hartloff tattoo. No, I might auto fail you if you get a Hartloff tattoo. That'd be a bad decision. That would be a poor life decision. So we want to add this to all inheriting classes. Even then, okay, we have two classes. I could write this method once and cut and paste it into the other class. It'd be gross. It'd be a terrible idea, but it would work. And it wouldn't be the worst thing. But what happens when we start expanding this game and we have 10, 20 different types of game objects that our players can interact with, and we want them all to detect if they're close to the player? Well, we write this once, and instead of cut and pasting it 20 times, we just write it once and let those classes inherit that behavior. One and done. It's easy. It's easy to write. It's easy to maintain. If we change this and we want to go with homework 1, the first project, and say instead of Euclidean distance, these are now locations, these locations are now lat longs, and we want to use greater circle distance. I update that once. I update this one method. Done. That's it. Done. I don't have to go to every single class. Those classes just automatically update because they're already inheriting this class. I should have clicked while I was saying this. But if we have many types of game objects, write it once. All game objects, everything that extends this class gets that functionality. But wait, there's more. In our GameObject class, which is extended and inherited by Health Potions and Dodgeballs, in this class itself, we can also extend another class. So say we want physics to be applied to this. We have some physics engine, which, in this section we don't. But say we had some physics engine, and again, I didn't delete some of my clutter on this slide. Just ignore the dimensions and input velocity. Did I definitely, maybe I only updated it here. But this code is supposed to be the same code over here. So say we have some physics engine that works with physics objects. And it's made to work with physics objects that have a location and a velocity. And it'll move the physics, it'll do collision detection and handle the movements and get nice parabolas if we throw and arc something in a 3D space. It can give us all kinds of nice features like that. And we only want to write that code once, but we want to apply to everything that we can imagine later on. Well, now, when we have this game object, which we're not thinking about our physics object, we haven't been thinking about physics the entire time throughout this lecture, throughout our design of this game, well, now, even as an afterthought, we can say, well, let's just have GameObject. Let me go back to the slide so the code's right. We can just have GameObject extend that physics object that the physics engine works with, have our game objects be physics objects, and inherit all of that behavior, state and behavior from a physics object. And now, guess what? Automatically, Health Potions and Dodgeballs, especially when throwing the Dodgeballs, we don't want to recreate how that moves through the space, through the game space. Let the physics engine take care of that. Just extend physics object, and now everything just works with the physics engine. The physics engine that we don't have, which would work with physics objects. Extend all that behavior, inherit all that physics object behavior, done. Put all the physics code and physics object in the physics engine, done. So now when we're writing our Health Potion and Dodgeball classes, we don't even have to think about the physics of our game when we're writing those. We just think about the game-specific functionality for Dodgeballs and Health Potions. How do they interact with players? That's all we cared about. But by having GameObject extend physics object, and then Dodgeball and Health Potion extend GameObject, which by the transitive property extends physics object, now Health Potion and Dodgeball have all of the properties, all the state and behavior of a physics object, and all the state and behavior of a game object. And they can get all of that functionality. Same name parameter made you lose track? Oh man, I'm sorry, Priest. So now that we know what inheritance is, we have these kind of base classes in Scala. Any, which absolutely everything inherits. Anything defined in any exists in every single object in Scala. Absolutely everything. Any is inherited by any val and any ref. So any val extends any ref extends any. All of these values, which I call primitives, all extend any val. And everything else, including every single class that you write, extends any ref. This happens by default. If you don't extend anything explicitly, your class implicitly extends any ref, just by default. So if all the classes we created without inheriting from anything, they implicitly extend any ref without you having to write it. So any class you write has all the functionality in the any and any ref classes. So your classes actually have this health potion actually has 5 different types. And this slide really is what polymorphism is, just to motivate Wednesday's lecture. A health potion can be stored in a variable of type health potion. Of course, potion 1 will store a reference to this health potion. But it can also be stored in a reference, in a variable of a type of any class that it extends. So we can store a health potion in a GameObject variable, a health potion in a physics object variable, a health potion in an any ref variable, or a health potion in an any variable. We'll see the implications of that on Wednesday.